Dear students, I am Dr. S. Balakrishnan from the Department of Physics. I am going to explain the concept of photoelectric effect and how to perform the experiment. Before we get into the experiment, let me explain few historical aspects. In the attempt of understanding the atomic structure, the discovery of electrons by J.J. Thomson and discovery of X-rays by William Röntgen made a very big milestone. Once the electrons were discovered, many experiments were performed, and the phenomenon of emission of electron from surface of any metal is known as electron emission. There are many ways by means of which electron emission can take place. Some of them are photoelectric emission, thermionic emission, field emission and secondary emission. We are going to discuss photoelectric emission in detail. Heinrich Hertz performed many experiments with electron, and he observed the spark between two metallic balls when a high frequency of radiation incident on it. This is called photoelectric effect. In other words, photoelectric effect is the emission of electron when electromagnetic radiation having sufficient energy incident on certain metal surfaces. We call the emitted electron as photoelectrons, and they constitute a current, and it is known as photocurrent. If you look at this schematic diagram, which helps to understand the concept of photoelectric effect. Here you have a metal surface upon which light is shine, and once the light of a suitable energy incident on the metal surface, then electrons are being emitted, and the emitted electron constitute the current, and that can be measured using the ammeter. And there are major observations in the experiment of photoelectric effect. First and foremost, photoelectric effect is an instantaneous phenomenon. There is no time delay is observed between the incidence of light and emission of light, and the energy of emitted photoelectron is proportional to frequency of incident light. However, it is independent of intensity of incident light. On the other hand, the number of photoelectrons is proportional to intensity of the incident light. These four major observations could not be explained by classical mechanics. So there is a serious contradiction between the observation and the theory. So in order to explain this, scientists come up with the new theory known as quantum mechanics. In the attempt of explaining black body radiation, Planck proposed a very revolutionary idea known as quantization principle. So as per the quantization principle of Planck, energy is not observed or emitted continuously, but it happens in the form of a discrete packet, and discrete packets are known as quanta. In the case of light, quantum of energy is called photon. The photon, which are the discrete packets of energy, are being emitted by the source of radiation. So the energy of photon is equal to E equal to h nu, where E is the energy and h is known as the Planck's constant, nu is the frequency of incident light. And the momentum of photon is happened to be P equal to h nu by c, which is also equal to h by lambda, where lambda is the wavelength of the photon. The rest mass of photon is 0. In order to explain the photoelectric effect, Albert Einstein exploited Planck's quantum theory, and he explained the observation of photoelectric effect. In fact, Albert Einstein received Nobel Prize in Physics in the year 1921 for his outstanding contribution in the understanding of photoelectric effect. Though we know very well Einstein is very much famous for E equal to mc square, he got Nobel Prize for his contribution in photoelectric effect. So as the experiment which demonstrated quantum theory of energy level, photoelectric effect happened to be a very significant experiment from the historical point of view. There are three major laws associated with the photoelectric effect. The first one is the rate of emission of photoelectron, which is also called as photoelectric current, is directly proportional to intensity of incident light. Below the threshold frequency, emission of photoelectron cannot take place. Above threshold frequency, the maximum kinetic energy of emitted photoelectron depends on the frequency of incident light. You will understand these three basic laws once we get into Einstein's photoelectric equation. Before we start, let us revise the important and essential technical terms. The first and foremost, the work function. The minimum energy that is required to eject an electron from the surface of a metal is known as work function of a metal. It is a characteristic of a given metal. The threshold wavelength is the wavelength that can eject an electron from the metal and this is also the characteristic feature. The threshold frequency. In terms of frequency, we can define threshold frequency as the minimum frequency of light that can eject an electron from the surface of the metal. The stopping potential is the minimum negative potential that is given to the anode, which can stop the photoelectron, and thereby the photocurrent becomes zero. So this is a very important term. We will be exploiting this for the understanding of Einstein's photoelectric effect. Before we get into the experiment, we need to understand what is the aim of this experiment, namely to determine the work function of the given metal, and we also wish to establish the Planck's constant value, namely h. So let us learn how to derive Einstein's equation of photoelectric effect, to construct the table, to plot the graph, and to determine the quantities. So let us get into the simple derivation. So here we have equation h nu is equal to k E plus W. What is this? So h nu is nothing but the energy of the incident photon, and we know very well part of the energy is utilized to knock out the electron from the surface, and that is nothing but W, the work function, and Ke is nothing but the kinetic energy of the photoelectron. So sum of the kinetic energy and the work function, which is equal to the total energy of the incident photon. Since the maximum kinetic energy of photoelectron is equal to stopping potential, we can replace the maximum kinetic energy Ke by E equal to Vs. So upon rearranging the term, we get the equation something like this. So Vs, which is nothing but the stopping potential, which is equal to h by E nu minus W by E. If you look at this equation, it is very much like a straight line equation, y equal to mx plus c, where m is nothing but the slope, which is given by h by E, and intercept c is given by W by E. And once we have the experimental parameters, namely the frequency and the stopping potential, we can plot a graph. So the frequency comes along the x-axis and the stopping potential comes along the y-axis. So if you plot the experimental data points, you get a straight line which passes through the negative y-intercept. Why we are getting negative y-intercept? Because we applied the negative potential. And once you calculate the slope of this particular straight line, you can equate it to h by E, from which you can determine the Planck's constant h. The y-intercept helps you to find out the work function of the given metal. So here you have the observation table. So once we have the incident photon wavelength, we can calculate the frequency using the relation c equal to nu lambda, where c is the speed of light, nu is the frequency, and lambda is the wavelength. Having the frequency, and we can perform the experiment for various frequency, thereby we can calculate the stopping potential, and hence we can plot the graph between the frequency and the stopping potential. Once you have the data points, you can find out the slope, from which you can establish the value of Planck's constant, and from the y-intercept you can determine the work function of the given metal. Having known the theoretical part, now we are in a position to learn the experiment. Dear students, here we have the instrument to perform the experiment photoelectric effect. Here you can see Planck's constant measurement instrument. Of course, the aim of this experiment is to measure the work function of the given metal and to establish the Planck's constant. So let us get into the instrumentation part first. So here is the box where we have the metal upon which the light source is going to be shed. And here you can see the circuit which is given over here, which is essentially incorporated in this box. So you can see that there is a symbol over here wherein we have the metal upon which the light is going to be shed, and we have a ammeter which measures the current in microamps, and the voltmeter which measures the voltage in volts. And we also have the potential divider unit, and we can change the potential by changing this knob. So let us get into the knobs available in this instrument. Essentially we have one display window wherein we can see the current reading as well the voltage reading upon changing this knob. So the current is measured in microamps and the voltage is measured in volts. And you have here the current multiplier wherein you can scale the current so that it can be measured within the available digits in the display. And here you have the light intensity can be increased using this knob. You can see the arrangement. So minimum to maximum that can be done using this knob. And we have this knob which helps to increase the voltage, and here you can see that minimum to maximum, you can see over here. And this is a very important knob wherein we can adjust the direction of the potential divider. So we can have either on the positive terminal or the negative terminal. I will explain the significance of this particular knob once we get into the experiment. Right. So what we have here, we have the metal and upon which light is going to be shed, and here you can see the light source. So this is the light source we have, and we have the metal over here and which is closed by this. So we are going to use the different filters, and these are the filters we have, various filters, and you can see the wavelength corresponding the filter. So let me keep the filter whose wavelength is something like 460 nanometers, and let me fix it. And you can see over here there is a scale, and I also have the provision to adjust the distance, and I can adjust the distance between the filter and the light source. So let me take a convenient value, namely at a distance of 25th centimeter, I fix this. So we kept the filter whose wavelength is something like 460 nanometer, and the light is allowed to fall on it, and initially the current should be measured like this. And now what I am supposed to do, from the theory we learned that by applying the suitable stopping potential I can make the photocurrent to be 0. So we have the option to adjust the voltage so that the current becomes 0. So let me adjust this knob, and so that the current becomes 0. Slowly you can see as I rotate this knob, you can measure the current and it keeps decreasing. So at one particular point where I can read 0, 0, and once I change this knob I can measure the voltage. In this case the voltage is something like minus 0.97. You might be wondering why I am getting this minus sign, because of the fact that we kept the knob in the minus sign. You know very well we want to stop the photo current, and in order to stop it we should apply negative potential because electrons are negatively charged. So once you measure this, you can make a note of this value. So for the wavelength of 460 nanometers we obtain the stopping potential of minus 0.97. Once you have taken the reading, it is always advisable to switch off the light, remove the filter, and go to the next filter. So I have the filter something like 500 nanometers, and keep the filter and switch on the power supply. Thereby you shed the light again. And note that the distance is kept fixed, and I am also not changing the intensity. So once you go to the next filter, go to the current mode, once again adjust the voltage knob, thereby you can reduce the current to 0. And once you make it to 0, then you can measure the corresponding stopping potential by adjusting this knob. So once again I move to the voltage side, and now the voltage is something like minus 0.79 volt for this particular filter. It is always essential to follow good lab practices. You can see here the power supply is on, and I have the control over the local power supply. So whenever I change the filter I should switch on and off. Otherwise you can see a toggle in the reading and you will get a very erroneous reading. So it is always advisable to switch off the light when you change the filter. That is first thing. The second one is, we have the filter in the increasing order. You keep it in the increasing order of the filters and you can perform. So if you perform the experiment randomly, then you can see the toggling of the reading, and it will take some time to settle down, and you will end up with a wrong observation. Another important point is, throughout the experiment you have to keep the distance fixed as well the intensity. So here you can see that I have a provision to change the intensity. So now the light is so dark, now you can see. Right, you can, in order to see the effect, you can come over here. So I have maximum and I can decrease the current. So now it is not a good advice to change the intensity and the distance when you perform the experiment. So for all the available filters, you should keep the distance fixed, and you should keep the convenient light intensity, and you should also keep the current multiplier at the appropriate value. So if you mismatch this for any filter, you will get a wrong reading, and because of which you will get a wrong observation and a wrong result.